Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks very much. It's great to be here and great to see all of you here in Seattle. So I'm here to welcome you to Seattle, and it's great to see so many of you here and so many new faces in the room. We hope we've got an interesting program, so let me carry on and tell you a little bit about it. So the goal of the summit is to network and with colleagues and friends and to understand the problems that are facing not only computer science but also how computer science can help solve some of the problems of the world. So we've got nearly 100 presenters, we've got 27 countries, 300 or so are people who have not regularly been to the faculty summit, which I think is an impressive number, and I'd be very interested to hear your reactions after the event, and from 170 odd institutions and agencies. So it's a really diverse group, and I hope you find it a useful exercise in networking and building relationships. The theme for the conference is embracing complexity, which, if you like, sums up the goal of computer science, which is handling complexity by abstraction and hierarchical design and so on. And we've picked out some of the major themes. There's a session on natural user interfaces, software engineering, of course, the future of the web, where web is going, semantic web, Web 3.0, Web 4.0. And then there's the cloud, which is actually going to change all sorts of things in industry, in the way we do things, in research, and also for consumers. And we're also seeing, and you'll find outside, some copies of a book called The Fourth Paradigm, which was a collection of essays about how the data explosion in most of the sciences is going to affect us all, and how I think techniques for computer science will be needed to help scientists manage the challenge of this data, to find the signals and to understand the events that are happening. So addressing global challenges, the graphic is about the Ocean Observatory Initiative. There's one of them off Seattle in Puget Sound, putting a fiber optic cable on the seabed floor, which will change oceanography from being data poor, you just have a ship across the surface getting occasional bits of data. Here you'll have data flooding in 24/7, 365 days a year. So large amounts of challenges, and I hope we'll have a stimulating discussion, and we'll see exactly how we can engage and collaborate in these areas. So my organization is called Internally External Research, but really it's about collaborating with universities, doing collaborative research with universities. And we have broad geographical outreach, so we have visitors here from Asia, from India, from Europe, Latin America, and each of these countries has a outreach program with universities, and of course they're all slightly different in each of the countries, and we view this as very helpful, and we try and get commonality where we can and diversity where it's appropriate. We've organized our programs. Obviously we have a core computer science activity, and that's really a major focus for the future of our industry. We believe that it's important that computer science departments continue to thrive, continue to produce great students, and that students are interested and excited to do computer science. And part of the way to do that is actually by showing how computer science can help solve some of the problems of the world. In Earth, energy, environment is one of the themes, and you saw the opening video about one of the projects we have in Latin America with the sensor network in the rainforest. Health and well-being is another major strand of our activity, where we're applying to the wealth of genomics data, for example, machine learning techniques are going to be essential to make understanding of that and to understand complex diseases like HIV, AIDS, and diabetes. And lastly, in addition to this data revolution and the ongoing revolution in computer science, we are in the midst of a publishing revolution when you can make free digital copies for nothing, and when you can actually publish it on the web yourself for nothing. That really changes the game, as newspapers and everything are finding. And so what does that mean for scholarly publishing? And how can we actually link the data to the publications, and what are the implications of that, and how do we store data so we can access it in 20 years' time, for example? So education and scholarly communication are an important theme, and you'll find that's one of the themes of the conference too. And the rest of my team, we try and work with the university community to try and build tools and software services which actually help them do their research. And so the goal is to work with researchers to try and produce tools, and at the moment we're doing them in open source, so we can extend them, you can extend them, you can port them to other platforms and so on. So that's what we're trying to do. These are our major disciplines, and this is where we focus our efforts. So what I'd like to do is take an example of how computer science and the technologies from computer science can actually affect some of the other disciplines. So what we're announcing today is the Terapixel project, which is available today on Worldwide Telescope. It's, I hope you can see here, this is the original image Worldwide Telescope uses of the sky, taken from digitized photographs of the sky, which produces overlapping regions. They're taken in slightly different exposures and so on, and the edges are slightly untidy. And it's around 3 million files and about half a petabyte of data. And so what we wanted to do was bring them all together, and actually these 15-year set of plates, could we make them into a seamless image that you can actually looks like the actual sky that you see. So in the moment, the state of the art is this individual tiles and seams, and what the challenge was, can we manage and manipulate that vast amount of data? First of all, to take from the raw data to create the color image, then you have to stitch and smooth them, and then you create the sky image pyramid that you can zoom in and zoom out for Worldwide Telescope. So that was the challenge, and to do that, what we needed to do was put together a bunch of computer science technologies. So on the left, you see creating the color plates and the various tasks you have to do there, then stitch and smooth the images using distributed gradient domain processing to smooth them, and then finally to create this pyramid. And the technologies that were used to do this, and it was sort of 6 months challenge, and it was, I would say, a grand challenge to produce an image this size, which is large numbers of HD TVs, many hundreds of them would have to accommodate this image. We use Dryad Link, which is a type of MapReduce, a slightly more general version of MapReduce. We used the .NET parallel extensions because we needed to do parallel processing to decompress the data. And then we used high-performance computing on a Windows cluster with Dryad Link. And the whole thing was orchestrated by a workflow engine called Trident that we produced. And putting all these different technologies together, they were able to process these 3 million files and produce a really impressive image at the end of the day. So I hope you can see a difference between these two images. If not, we've failed. But that was what it was like, and the final image is really very impressive. 500,000 high-definition television sets, it tells me, you need to view this. So it's a large amount of data, and you can access it from your desktop and zoom in and zoom out. So I do encourage you to go and try Worldwide Telescope with this new data and get lost in space. Right? So it's really good. So that's Terapixel. What I'd like to do now is announce the official release the Apogee release of Worldwide Telescope. It's a new release. It has all sorts of cool things, exciting things like the asteroid belt, and you can do amazing things with it. And in just a second, I'll introduce NASA's Chief Technology Officer for IT, Chris Kemp, with whom we collaborated with NASA on taking their Mars data. But first of all, I'd like to show you a brief video. So could we roll the video, please?
Years ago, in working with Chris Kemp from NASA, we started thinking how we could bring together the features and the functionality that we had in Worldwide Telescope to some of the planetary data sets. And we really wanted to focus on a unique asset, the high-rise imagery that Mars had. And so we started working and collaborating to figure out how we could bring to the public and get it in their hands. The high-rise imagery is a one-of-a-kind camera that's on board one of the satellites that goes around Mars and takes really high-resolution images of the planet's surface.
We have complete base maps of Mars as well as very high-resolution data that are actually higher resolution than most of the satellite data that is publicly available of Earth. And so we can actually see Mars in better detail in some areas than we can see Earth.
This project leverages several teams within NASA and then also, of course, teams at Microsoft. And really, it's bringing together some of the kind of cutting-edge technologies in both institutions to do something which has not been possible before.
People can go for a walk on Mars now and actually see the craters, see the cliffs, and get appreciation of the scale in a way that they could never have done before.
Mars is a big place. By making this raw data, this full high-resolution data available in Worldwide Telescope, we're just going to open all of that up to classrooms across America, across the world, and connect with the public in a way we've never been able to before. So if we can really put projects like Worldwide Telescope in data sets like the Mars high-rise data set, I think we could inspire the next generation of Americans, like Apollo inspired this generation of Americans, to really be innovators, be thought leaders, and be leaders in the world.
Okay. Thanks, and now Chris will tell you really about it. Chris.
Hi, thanks today. We're really excited about the release of Worldwide Telescope Mars. This was a really exciting project. We started working with Microsoft Research about a year and a half ago, and teams from NASA that were responsible for doing all of our data processing for our lunar data sets were looking at ways to make that data more accessible in platforms that had more reach to the public. And so one of the things that we wanted to do is ensure that we were able to connect with classrooms, universities on a platform that was extensible and accepted by millions of people worldwide. So what you're able to see today in Worldwide Telescope when you zoom into Mars is the largest digital image mosaic ever created. The technical challenges for this project were immense. We have almost 15,000 terapixel images, so over 1 billion pixels per image. Each of these images is, of course, too large to download, so we worked with the Microsoft team to develop a high-resolution projection format. Unlike those in other projects like NASA's own Whirlwind project and other commercially available geospatial browsing platforms, the Microsoft Worldwide Telescope platform does not break down at the poles. And the poles are some of the most interesting regions on Mars. So we saw this as an exciting opportunity to create a platform that was much more scientifically accurate and useful as we look at some of the more interesting regions on the planet. We developed our image processing pipeline to run in the cloud, so we were able to take these 15,000 terapixel images and turn them into almost 500 million smaller PNG images that are progressively downloaded when you connect to the product and you go to an area. So as you're zooming in, you're actually only downloading the image content that you need to see whatever particular region of the planet is on your screen. The other really interesting technical challenge was applying extremely high-resolution terrain map to the surface. No one's ever really zoomed in as far as we were allowing folks to zoom in. So as we zoomed in, we actually had to work really closely with the Microsoft team to optimize some of the 3D algorithms in Silverlight to render the ultra-high resolution terrain maps without any visual image artifacts. So this was a great example of a public-private partnership that resulted in a massive data set that was always available on the web if you wanted to download terapixel scale images from a JPL website. But by making all this content accessible in Worldwide Telescope, we're making it accessible to classrooms, to labs, to scientists that want to build on top of that existing platform. And I really see this as the future of NASA's data architecture, whereas instead of focusing on building end-user applications, the government is a platform, and we're working with organizations like Microsoft Research to develop standards to deliver the data so that it can be consumed by the scientific community. So it's been a fantastic collaboration. I appreciate the opportunity to work with Tony and his team, and there's more to come. We have lots of data. Cheers.
Thanks very much, Chris. No, that was, it's a very exciting collaboration for us. We have a NASA Space Act agreement, and we hope there's lots more good things to come. So it's a great collaboration. So that's applying computer science to solve some of the problems of, in this case, displaying astronomy data. What about computer science for computer science sake? Well, what we've also got is a service called Web Ngram. It's now in public beta, and its intent is to advance research in search and what goes beyond research and beyond search, and you'll hear about that in one of the parallel sessions today. To do that, researchers need access to real-world, large-scale data and to be able to data and compute on this data. So what we're trying to do, we've been struggling with the problem that privacy and anonymity of data are critical, and therefore what we're trying to do is make this available to the research community, access to web-scale data via data services. So this is the Web Ngram service, which is to help advance research and experimentation in all sorts of areas, such as speech, learning, machine translation, as well as search. And so what's it about? Well, it's about this. Users usually have a query on a single word, and the blue lines there show single word, bigram, trigram, and fourgram the distribution. But search engines typically only search on unigrams, and so what the distribution you get from a search engine is not the ideal distribution that you would normally get. And that's partly because there's more information than just the body of the text of the web page. There's the title and the anchor, and all this context metadata is typically ignored. So this will be the subject of a workshop, as you see there, in Geneva later this month. And those of you who can have the opportunity to go to Geneva, I like the town very much. I used to live there, so I do recommend that you go there. And also the conference will be interesting. So let me just give an example. What was really good, well, we announced this at the last World Wide Web conference in Raleigh, and within 8 hours, Dr. Ding at RPI had produced this multi-word application. So you can see on the left a single tag cloud, and you see the usual from a body of government data he was using, and you see it picks out a number of tags. But you get much more information if you use the engrams. So you see critical and habitat, but you see they come together in critical habitat, and you see also things like toxic release inventory data. There's a foregram, and that's extra information that can actually help make clear the user intent much more than just searching on single words. So large amounts of things to be done. This is free for non-commercial research. We have a petabyte of data there up in the cloud, and it's assisted by our ISRC team, the Internet Services Research Center, and they've been very helpful, and you can collaborate with them. And it's available on Azure for people who are participating in the NSF program for computing in the cloud. And it's a collaboration with Bing, and Harry Shum will be giving a talk later today about the collaboration with Microsoft Research. So that's an example of actually doing something for the computer science community. So we don't just do things for the environmental science and health communities, but computer science is an important area for us. So where are we? Well, I'm standing in the way between you and an interesting program. So we are going to announce tomorrow the new faculty fellows for this year, and we have a little presentation with Rick Rashid, and I invite you all to that. Today we have a number of exciting plenaries and themes sessions. So we have themes in natural user interface, data-driven software engineering, challenge of large data, future web, and there's Design Expo. And tomorrow we have operating in the cloud and Demo Fest, as well as some special topics, and the special topics are also extremely interesting in my view. I have difficulty deciding which ones I can dip into. But the plenaries I hope that you'll all enjoy. So the first plenary we're coming up to in a moment is the innovation of what used to be called Natal. It's a great collaboration between the Xbox team and Microsoft Research. Several of our labs participated in that, and you'll hear about that in the next talk. Then we have this year's Turing Award winner, Chuck Thacker, who essentially was one of the pioneers at Xerox PARC for the infrastructure you see around you, the PC with the mouse and the keyboard and the graphics screen and so on. That was all developed by the Alto team, of which Chuck was one of the major leaders, along with people like Butler Lampson. So Chuck will be giving a talk, Rethinking Architectural Research and Education, and then tomorrow morning we start with a panel chaired by Rich DeMilo, with people like our very own Ed Lazowska, who's sitting in the front row, who will be there tomorrow morning, along with others from around the world. And finally, we finish with what I hope will be an exciting talk about the making of Avatar, and I assume most of you have now seen Avatar in 3D. And the interesting thing is whether Justin Ratner gave us a talk at Supercomputing last year, and it was about the 3D internet, and he clearly sees that 3D is a major part of our future. Well, and that's what Hollywood think. So it'll be interesting to see exactly what this audience thinks of that. So there's if you want to tweet, that's the symbol you use. There's a dinner cruise tonight, and I hope that you'll enjoy the networks and be able to leverage the space. We've tried to make it a little less structured than last time, so you have an extra amount of time that you can, which is not taken up and organized for you, you can use for whatever purpose you like. So hope you have a great time, and what I'd like to do is finish here and introduce our next speaker, who is this year we're focusing in our computer science theme on software engineering and programming languages, and Judith Bishop is leading that activity, but we have a new activity on natural user interfaces, which is being led by Chris Toll. So thank you very much for listening, and I'll introduce Chris Toll in just a moment. Thank you.
Thanks so much, Tony. I have the great pleasure this morning of introducing our first two keynotes. And they're going to be talking about Kinect, the technology formerly known as Natal. We have two speakers this morning. One of our speakers is actually from the product group, and it's going to give a nice product perspective of it. And our other speaker is actually from Microsoft Research. So we're going to start out with Kudo Tsunoda, and he's our creative director and general manager for 3 studios inside of Kinect. He has 13 years in the computer games industry and has several #1 titles to his name. And as such, he brings a great breadth of knowledge and depth of understanding and innovation to a technology that is going to not only change computer gaming, but even natural user interfaces as a whole. Following him, we're going to have Andrew Fitzgibbon. Andrew is a senior researcher in our Microsoft Research Cambridge lab in the UK. He has actually twice won the IEEE Mars Award, which is the highest honor in computer vision, and an Engineering Emmy for significant contributions in the creation of complex visual effects. His most recent work has actually been in the recovery of 3D geometry from 2D images and human 3D perception and separation from different individuals inside of a scene, as well as separation from the floor. So it's my great pleasure to welcome and introduce our first speakers, Kudo and Andrew. Thanks so much.
All right, thanks. So I'm Kudo. Andrew's still backstage. I'm going to be introducing him in a second, so there he is. Awesome. So, yeah, again, I'm Kudo. I'm the creative director on the Kinect project. Just wanted to come out and give you a quick overview about, just from a creative perspective, how we approach Kinect, what the working relationship was with MSR, and some stuff like that. So some nice things we got going. Our PowerPoint also Kinect enabled, so that's awesome. Bam. There you go. So, oh yeah, quick introduction. There it is. I just did that. But I'm the creative director on Kinect. You could tell from my introduction, apparently I was trying to juice up my own resume, even here at the MSR talk, and put 15 years of gaming experience versus the accurate 13 that Chris said during my introduction. But as long as all the time I was working in gaming, I worked at like what we call third-party companies. So companies outside of Microsoft where, you know what, they make a great platform like Xbox 360. You get this platform, you get this controller, and then, you know, just as a creative person, a lot of what your job ends up being is you have kind of an idea in your head of how you want a game to work or a consumer experience that you want. And you kind of have to like shoehorn it into whatever platform that, you know, a company like Microsoft or Sony or Nintendo gives you. Because as third-party, you know, creative, you can't work with the platform team. You can't work with, you know, anybody at the company to actually help drive what the platform is. And that's, you know, I've been here at Microsoft now for less than 3 years, but it was one of the most exciting things for me about coming to Microsoft is that instead of having to like work with an existing platform, you could come here and work with, you know, the people who are actually making the hardware or making the software that runs the hardware, so that when you have an idea in your head, you can just try and actually work on something that will enable that creative instead of forcing it into the existing platform. And it's interesting, like all the games I've worked on in my life before all had something to do with gesture-based controls or trying to make things more approachable on the existing controllers. So I worked on a boxing game where, you know, you're trying to throw punches. Instead of pushing a button to throw punches, you take an analog stick and you'd move the analog stick just the same way you wanted to move your fist. So if I wanted to throw a hook, you move the analog stick out to the side and then arc it forward, because that's the way you throw a hook in real life. But that just shows you kind of how rudimentary it needs to be, you know, gesture-based controls or things that you're trying to do to make games more approachable on an existing controller. And it was one of the big reasons of getting to, you know, wanting to come to work here at Microsoft, is just getting to partner with people on the platform team, people at MSR, a bunch of really smart people who are much smarter than me, to try and get some things done to actually help enable the creative we're trying to do. And so again, just want to say I'm the creative director, so if you have any hope that I'm going to explain to you any of the technology behind this, you are sadly mistaken on that one. Like, I've done a bunch of talks about Kinect, and any time there's a technical question, I just kind of fall back on, yeah, you know, that's the magic of infrared, and most people aren't technical enough to know anything about infrared, and so everybody just nods their head yes and is happy with that. So no technical questions for me, please. I'm the creative director. So, okay, good. So give you a little quick background on how we started for the Kinect program from a creative side. So, you know, really the first time I saw any of this stuff, somebody came in with one piece of the hardware. We didn't have any software to run anything. And they kind of had this, hey, look, this sensor does a 3D depth map, and you can kind of track people in a very rudimentary fashion. And that was all we really knew. And, you know, again, not being very technologically savvy, you know, we just start from a creative perspective, trying to set some kind of high-level goals. And the thing that's been really interesting to me about the whole Kinect journey is just seeing how the high concept creative goals that we started with, ended up matching a bunch of technology that people were developing, and then how we can combine those things together in a compelling way. And so we really started with Kinect, just trying to make Xbox something that is more approachable to more people. If anybody has seen an Xbox controller, it's got like 832 buttons, like 5 analog sticks, a whole bunch of shoulder triggers, and it really takes an enormous amount of manual finger dexterity to be able to play any of the games. You know, I've played games since I was a little kid, and yet still every time I get a new Xbox game, I kind of have to sit there with the controller and try and figure out, you know, retrain my muscle memory on how to play the game. And so I'm willing to do that. I love games, but lots of people, you know, hey, Xbox, our main slogan is jump in, but it really isn't very jump in, right? You got to like deal with this controller. Somebody hands you a controller. It's kind of, you don't know what to do. You sort of get embarrassed and you feel stupid. And like, you know, that's not a good like first introduction for people to Xbox. And, you know, especially unless you want to like feel stupid and embarrassed in your own home, you're probably going to not go out and buy an Xbox if you played it at a friend's house so you could get those same feelings in your living room. So we really wanted to focus on how can we make it more accessible to people? How can we get it so anybody can jump in and play and not have to worry about reading any instructions? And so before we knew anything about any of the technology or how things are going to work, you know, somebody like me just sits in a room. Oh my gosh, I've got a presentation to some executives in a couple days. Hey, we're going to come up with this great idea. It's making Xbox more accessible to other people, and hopefully it all works out. Bloop. And so we started to develop some key pillars. And, you know, as a creative person, I often find that my job or my, you know, kind of work responsibilities are to make up a whole bunch of stuff that isn't true and then leave it to everybody else to figure out how to make it like actually happen. And hopefully like the stuff comes together like in the way that you made it up at the beginning. A bunch of smart people can go figure out how to make that happen. And before anybody finds out that I just made it all up, somebody's actually figured out a way to deliver it so that it all, oh yeah, that actually came to be true. And kudos wasn't just telling us a bunch of stuff in a PowerPoint at the beginning of the project. So these were kind of the things that, hey, we hoped this would come together in the experiences. We hoped the technology would support it, but we didn't really know. Bloop. So first, we just wanted to build stuff that was unique to our platform, right? So, you know, lots of times when we started talking about Kinect with executives, there would be this international signal for what Kinect was. And it was an executive going like this, right? Because there's no controller, I can just move my hands around, and wow, that's a Kinect game. And like, at the end of the day, those are very similar things that you can do in existing platforms, right? You could already do it on the Wii, you could do it on the PlayStation Move, and what we wanted to do is figure out a way, okay, look, we want all of our experiences to be something that really can't be done not only on any other console, but on any other medium. So the next one, I appreciate the camera click, right, as I got my fireball motion down. Hopefully that was very nice. So again, trying to make it approachable so anybody can get in and play, whether you're a kid, whether you're an adult, no matter how much gaming experience you have, how old you are, you can just jump in and play right away. And we really tried to focus on doing things that came naturally to people. And what, you know, ended up being interesting was just, yeah, what's natural to one person is totally different than what's natural to another. So getting things that are natural to everybody, super interesting creative challenge. But hopefully you'll see in the experiences how we worked that out and that actually came to pass. Thank you. So social, you know, and this is something that I just think about gaming now. You know, it's just too bad when, again, not meaning to date myself, but, you know, when I grew up playing games, starting to sound really old, but when I grew up playing games, you could go to the arcade, you know, or doing stuff in your own house. It really was a much more social and fun experience in the way that, you know, my life evolved around gaming. And somehow gaming kind of evolved into, yeah, we've got Xbox Live and people play multiplayer. But, you know, what social is in gaming today is, wow, we're all in the same place killing each other, which actually killing people, not a very social activity, it turns out, at the end of the day. It's kind of a very competitive, you know, people getting angry, trying to shoot each other, talking a bunch of smack. And it's like, it's just not a very, like, inclusive kind of experience. And so we wanted, with all of our Kinect experiences, to do something that started bringing people together. And, you know, you could tell in the way the Kinect name evolved, that's just something I just think, if you start looking at technology and all the technological innovations that have happened in recent years, you know, people say, oh, it's social media or things like, you know, Facebook or whatever is bringing people together. But really what it does is it starts like creating a one-on-one relationship between people and technology that is very isolating. You know, I mean, sure, for somebody that I haven't talked to in 30 years, maybe it's more social on Facebook between me and them. But, you know, for me and my family or things or friends, now it's just like, hey, we're posting stuff on a wall somewhere and then they come and get it later. We actually end up interacting a lot less. Or you go to parties and dinners and stuff and people are just sitting there like madly texting into their phone like this. It's like really eliminating a lot of the human-to-human interaction. And it's something we wanted to do with Kinect to bring back to gaming, something that actually brought people together into a fun and collaborative way where like the actual personal relationships and the way you communicate with each other is a main part of the experience. So, yeah, so another one just being we wanted to make it a lot more fun to watch people playing. So you think about games today, you're just sitting here, somebody on a sofa kind of twiddling their thumb. It's not very engaging. And so we wanted to get a gaming experience where if you see somebody playing, wow, it looks super awesome. You want to be like laughing in and joining in, even if you're not playing, but then also like making it so you want to get in and try it yourself. And then the last one, just playing any way you want to. It's one of the things I hate about games in general is that, like, really you have to play the game the way the designer tells you to play it. Like, there's usually a level, there's a pattern you have to go through, and that the whole game experience is just playing the game the way the designer wants to. But we really wanted to enable Kinect experiences to let you play how you want. And so those were kind of the creative principles that went into things. We didn't have any technology to enable any of this, but in typical creative person fashion, you're just like, whatever. Some technical people will figure out how to make all this happen. All I got to do is write the slides on the PowerPoint. That's the hard part, obviously. So let's just get those down and hand them off to someone else. Psh. Oh, shoot, and there's one more. Redefining Microsoft's approach to broadening. This was kind of just a joke I would put in as we started showing the Kinect technology around. In Xbox, we've been talking about broadening for a long time. And then usually, well, okay, the controller's a barrier. So, hey, I've got a great solution. We're going to make the barrier pink or light blue. And then awesome, girls are going to love to play with the controller now because it's pink. So that's going to make it a lot more approachable and easy to use. So, yeah, it was really funny. I used to tell that joke all the time. And then not last holiday. Yeah, last holiday, the guy who made the pink and aqua controller sent me a whole crate of them with a not too pleasant message. So I haven't been able to use this joke for a while, but I figured we could do it here. He's probably not watching, so that would be okay. But anyway, the creative principles, that's Kinect. Again, no technology, but don't worry, it'll work out. Psh. So, oh yeah, here's a video that was our original high concept video of the experiences we wanted to enable with Kinect. And hopefully there's audio. Audio on the video. Kinect enabled. Audio, play. So these are just some of the experiences that we kind of just concepted together. And while, we use this video for a pitch and asking for a ton of money for this stuff, really none of this was actually working. This is just some dude standing here pretending to drive with gameplay that's being captured. But at least you could kind of see what the fun of the experiences were going to be, how the controllerless stuff works. And then you know what, you're going into a presentation at Xbox and you want to pitch something for money, it's good to put some Halo in because they love that Halo game and it makes a lot of money. But you could kind of see what we were going for. Again, none of this stuff worked, but hey, we're just trying to set a creative target and figure out how to do it later. And this is stuff that, eventually we did get up and running in other games, but at least you could see it looks fun, it kind of fits the creative principles, it couldn't be done on any other platform, it's full body.
Yeah, I think we could be.
And there was our super approachable Eye of Scion, which was going to be the whole branding behind Kinect. Really fun and approachable. And we're like, hey, wow, you know what? Everybody really likes the Wii, and that's doing well, so we'll put some Wii video clips in and make something about how Wii is super approachable and why aren't we doing that, and that should be awesome. And then who doesn't love a little Total Recall video? Anybody who remembers that from the movies in the old days? But we're trying to make the point of how with Kinect, we could actually teach you real-world skills or stuff that'd be helpful in your actual life. As it'll be the first time gaming actually helps you with things outside of gaming.
There you go.
Oh yeah, and this was just going to be how exciting our UI was going to be. So we put in, Minority Report, who doesn't love that movie? It's very entertaining. And then we realized kind of late in the video making process that our video was really short. We're asking for a lot of money, so we just looped a whole bunch of Minority Report in to fill time. It goes on for like a minute with Tom Cruise waving his hands around. It looks very exciting.
Sent you a party invite.
Oh, and here's our new experiences we're going to enable. totally new. Hey, DB, long time no see. You got time for a little catch? Sure do. All right, let's get it on. Oh, check out those effects. Holy cow. The football's coming out of the TV. Oh, it's great out here in the West Coast. Somebody at MSR will figure out how to make that happen. That's no problem. Sure will. Yeah, that's going to be a super fun one. We're going to have stuff flying out of your television, and you can talk to your friends all over the world. Awesome. Here's another one we had. It was called the world's longest jump rope. So you'd have one person in Seattle turning a rope, one person in New York turning a rope, and then over live, everybody could jump in between. Holy cow. Look at that. That's pretty awesome. Kinect's going to be great. Give us a lot of money. Come on. I can see Kinect technology is so amazingly powerful that it allows me to be turning the rope in Seattle and somewhere else jumping in the middle of the jump rope line. Holy cow, Kinect's awesome. Yeah, we were really on the cutting edge back then with our creativity.
Oh, you're leaving. Yeah, well, I got some stuff I gotta do too, so see you later.
So not only do we have the evil red eye of Scion, but it was like had a bitter emotional personality that got mad at you when you left also. So really awesome creative. I'm the creative director, put that together. We're like, oh, trust us, Kinect's gonna make a lot of money. It's gonna be great. But actually, you know, at least even in those stages, you could see there's at least some fun that you could get out of the program and the things that we're doing, controller-free gaming. There's opportunities for new things you could do. And again, we're just hoping at that point that somebody will go figure out how to make any of this stuff happen because it seemed exciting and we promised everybody we could do it. Bloop. And you know, that was the fun time where it's like, hey, we go from our little creative principles in our video to actually starting to work with people on the technology side. And you know what? Thank goodness that a lot of the stuff we just made up at the beginning actually stuff that was able to come to fruition in the program. And it's like just super great work by everybody who, you know, worked on the platform side, worked on the technology side to make this stuff happen. And so the features that we're using. So avateering, and you're going to see this in all the experiences. So that's all the full body tracking, right? And you know how the full body tracking works. Andrew will come out and explain the whole process of that. But it's really one of the, you know, the biggest feature of Kinect. It's the stuff most predominantly used in the games. It allows things to be approachable because, hey, if you know how to move your body, you're going to know how to play the game. You can play any way you want. It makes it fun to see other people playing. All this stuff that really comes to pass off of the full body tracking, or what we call avateering. And like out of everything, I mean, it's amazing that that thing works. It's super fun. We used to do UR sessions where people would just stand there with their avatar. We're trying to get game data, and they're just dancing around with their avatar, having a great time. And we're like, please, we need you to get in and start playing the game because we're trying to get some test data. And they're just having so much fun controlling their avatar on screen. It's just enormously compelling for consumers and everybody who touches it. It's just been great technology. And again, just amazing it works. Bloop. You know, other stuff we use for sure is a lot of the voice recognition and party chat. So obviously voice rec, I mean, shoot, they have voice rec today. You can say stuff into your phone and it hardly ever works and it's super frustrating, let alone the challenge of like, oh, by the way, we want voice rec to work from like 3 or 3.5 meters away, with a bunch of ambient room noise going on, a bunch of explosions and game noise coming out of the speakers. I still remember the day that we went and started to talk to people about that feature working. They're just looking at us like, yeah, you are nuts. There's no way in heck that's ever going to work. And yet still, people figured out how to make it come to pass, and it like is a really compelling feature of our games. And so, you know, you can interact with your Xbox now just using your body, using your voice, just like you interact with people in your everyday life. It's just really leaped us ahead of any of our competitors. Again, not only in video games, but anything that's being done in any medium. Recognizing people and objects. You know, we had everything on this from being able to stand in front of the sensor and get automatically signed into Xbox Live, as well as being able to digitize in objects. Like, hey, I'm going to hold up my water bottle, and the water bottle can go into the game. We've had teams that have been able to get the digitizing objects into games, but a lot of the stuff we've been using is recognizing people, not just for signing into Xbox Live, but you know what? Just being able to have characters inside the games recognize who you are as an individual, remember its relationship with you, you and the things that it's done with you. And it's the first time in video games now where in-game characters actually have like a shared set of memories and a shared set of experiences with the person playing that it can draw back on. And so that's stuff that has been super compelling in our games, and you'll see that in one of the demos we got today. And then, yeah, the last feature, and you know, people laugh when I say this, but it really is just a huge feature of the program that this stuff actually works. Like, it's a miracle. And like, you know, when we used to go around and show the demos at the beginning stages, that's just everyone would say, holy cow, I can't believe it works. And it is true. It's like such a giant feature of the program. It's amazing technology. It's stuff people have never seen before. Almost everybody who sees the stuff online or in videos, like, it's not like we're faking every video that we put out there, even though I just showed you a video that we faked at the beginning. But people like go, oh my gosh, I think it's fake. And then they get in and play, and it's like, holy cow, it's amazing that it works. So it just is a huge, compelling feature. It is amazing that the stuff actually works. So on that note, this is like a very first UR video I wanted to show you of, you know, the difference of going from our videos to getting the technology in. This is one of our first prototypes. It's a game called Burnout, and we really wanted to test that anybody could play without instructions. So it's a little kid, Noah. He's trying to figure out how to play. We didn't tell him what to do. He never saw Kinect before. He never played Burnout. And we're just like, hey, figure out how to drive. And there is audio somewhere. Oh, yeah, sorry. Audio play. Oh, well. It does work, trust me. Oh, there it goes. So you can see he's kind of fumbling around, trying to turn the car on, doesn't know exactly what to do. Up, whoop, something's going on with his feet.
It's like I ran over some. Ah! Oh, cool, gas pedal.
So like 50 seconds with no instructions, the kid could get in and already figured out how to drive and to start playing the game. And you think about how that would happen if somebody just took a controller and tried to actually learn how to drive? I mean, how do you drive with a controller? But everybody knows to turn a steering wheel, and the stuff that he could do with his feet was quick enough to learn on the acceleration. And then by the time his mom gets in, again, she only saw him go once. So simple to get in and play. And this is just the big difference between a bunch of videos and PowerPoint slides that we make up. And this was like the very first time that we had technology in and running and the stuff was actually working. But it's just so nice, like getting to see this, all the things that you like, the first glimpse of the stuff you made up in a video and the stuff you made up in a PowerPoint actually coming to life based on the awesome technology. Okay, ready? We're going to go. Bloop. All right, so those were some of the creative principles that we had at the beginning. I wanted to show you, how those things come together in our actual products. So we got two to show you. The first one is Connected Ventures. And this one really uses a lot of the full-body technology, the approachable stuff, making it fun to play and watch. So I was hoping we could bring up a random volunteer from the audience to play with me. So who would like to come up? Come on, somebody. It's early in the morning. Okay, excellent. Thank you. One person raised their hand. It's very nice. Let's give her a big round of applause. So you can see here, using the full body stuff all in the menus. Come on up. Whoa, are you all right? That's okay. Yeah, thank you. I'm Kudo. It's very nice. You made a good entrance. You sure maybe you want this side of the stage for when we're playing? Yeah, here we go. No, it's okay. You'll be all right. Don't worry. So this game, Connected Ventures, it's got a bunch of different activities, but this one is called River Rush. So you and I are going to move side to side to steer the raft. We're going to jump, and this is one of the ones that really the collaboration is important. So I'll probably be a little bossy since you haven't played before, so I apologize, but I'm going to give you the left, 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 right, 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 and try and help you through the course. All right, so there we are in the raft. You can see anything we do with our bodies, the avatar instantly does on screen. And we're going to jump to start. You ready? I'm going to do a countdown. 3, 2, 1, jump. All right, off we go. So we're going to steer a little to the right, head for that ramp over there. We're going to go up here, get ready, jump. Very nice. One more jump, jump. Perfect. All right, we're going to steer to the right. We're going to go up this ramp over here. Ready? You jump. Very nice. One more big jump. Okay, beautiful. We're going to go up this ramp. A picture is going to get taken of us, so get in a good action pose. Perfect. And so those pictures will come up through the game. You can post them to like Facebook or to the internet afterwards so you can share everything with your family and friends. Let's go to the right. Very nice. We're gonna go up this ramp, big jump. Awesome, you're playing great, thank you. One more big jump, get up there. Another one, our photos. Awesome, my microphone just went flying and hit me in the face, that's great. Okay, we're gonna go through these. You need to steer for a while because I'm putting my microphone back on. Okay, we're gonna go up this ramp. Ready, one more big jump. Ready, jump again. One more jump. We didn't really need to do that one, I was just joking around with you. Make you jump a lot. Here we go, we're gonna go up here now. Good jump. Get those big pins, we gotta steer to the right in the air. Hopefully we can land on there, very nice. Big jump. Okay, perfect, you're doing a great job, by the way, thank you. Now let's go left, we're gonna go through these pinwheels, get ready for a big speed burst. All right, we're heading down. There's gonna be one more big jump at the end. Off the waterfall. Here we go, we got one more picture. Very nice. You did an awesome job. Let's give her a big round of applause. And so you can see all of our pictures. And so cool thing is like we use the full body tracking combined with the RGB to figure out like what the names under the pictures are, so they actually match what you're doing with your body. But you can see she never played before, came right up and was able to play, knew what to do right away. Very simple, no instructions. If we had come up and I'd handed her a controller and said, oh, go play this game, like there's no way she would have known what to do. But it's so easy to get in. As long as you know how to move your body around, it's totally approachable. It's social, we're working together. It's fun to watch people play. All the stuff that we had at the very beginning of that, in our PowerPoint deck actually was working in the technology. So our next thing, this is a demo called Kinectimals, or a game called Kinectimals. Very different than what you just saw in Adventures. Not as physical as an experience, but still uses a lot of the voice stuff, a lot of the human recognition stuff. All right. So this is all about building an emotional connection between you and your animal, and you can adopt different animals from around the world. So this is only, 2 that we start with. Cheetah or an African lion. I'm going to take the cheetah. And then you can name your animal. So, Owen. Owen. Okay, good. So his name's nice and in. We'll go into the game now. And so it's cool because, again, the animal will recognize who you are. The animal reacts different to different people based on how much time you spend playing with him. All right, come here, Owen. Come here, Owen. Oh, very cute. Come here, Owen. Good boy. Oh, what are you doing, Owen? Oh, Owen, that's gross. Get that cleared off. Okay, come up here, Owen. Come here, boy. Come here, boy. All right, good boy. And so you can see this combines like both the voice technology, the full body tracking. Over time, as you do different things with your animal, like it'll become more familiar with you and react differently to you, so that just like a real pet, if I adopt this animal and play a bunch with him, if somebody else comes in to play with my animal, it's going to react totally different to me than it does to a total stranger. Good boy, Owie, good boy. And so get a nice little time, just start building up like the emotional connection with your animal. Great facial reactions on the animal, everything working together, the art, the technology, just for a nice, simple experience. Okay, tricks, Owen. We're going to do tricks. Okay, so now I can go in and start teaching my animal tricks, like, Owen, jump. Oh, come on, Owen. You could do better than that, Owen. Ready? Jump. Okay, one more, Owen. Come on, jump. Okay, one more big trick, Owen. Come on, jump. Oh, very nice. And here you can take pictures of your animal, share them out on the web. So all different types of tricks you can do. So I could do a, hey, Owen, turn around. All right, good boy. Owen, roll over. Roll over. Good boy, Owen. We'll see one more. We're going to try a Let's see. No, let's not do raise. Oh, try this. Come on, Owen. Play dead. Play dead, Owen. All right, Tim, we can cut it off. So that's, again, pretty much anything you do with your body, the animal will instantly do on screen. You can go into different activities, play like up to 30 different kinds, like run them through an obstacle course, play fetch, frisbee, catch balls, jump rope, a whole bunch of stuff. But it's like all different, two totally different types of experiences, but really all of them using the great Kinect technology, but also hopefully fulfilling at the very beginning the things that are unique to our platform, super approachable, anything you're doing with your body, let's not go into the final thought slide yet. Very social, fun to watch people play, and then being able to play any way that you want. So very good, and they're giving me the hey, hurry up and talk faster. So I'll get done with my demo, and I'm going over here for my Jerry Springer final thought segment. All right, so I guess nobody watches Jerry Springer, huh? Didn't get my Jerry Springer joke. So okay, we're here on the final thoughts. So, definitely the learnings about everything we've gone through on this Kinect NULL kind of journey is one, the work that we did has been incredibly hard, and it's been done in a super short period of time. And it's one of the things that I find interesting about Microsoft in general is that, really, groups in the company and different parts of the company don't always collaborate as well as they could. And it's hard to get a bunch of people in different countries and different groups and different parts of Microsoft all to work together. But when we do, wow, we can really make something super compelling. And I remember when I did my very first Neo training, and they had this thing called the Human Thundercloud. And so it's 150 people. You're sitting there for a day and a half going through a whole bunch of legal stuff and websites and whatever. And then in the middle of it, they get everyone to sit there and slap your legs and snap your fingers and make all these different noises. And then at the end, it's they put it all together and it's hey, you're a human thundercloud, and look at the power of everybody working together. If only we could work together, you could harness the power of a thundercloud, and how awesome that is. And after a whole day and a half of Neo training, I'm just oh yeah, great, you're human thundercloud. Thanks for making me do that. But at the end of the day, it totally is true, and this is one of the first things that I've been involved with at Microsoft where really there was such great cross-group collaboration and people working together to make something amazing. And so, sometimes you're making something hey, this natural experience we're doing with Kinect, it takes unnatural things to do it. People worked really hard, but again, very collaboratively, which isn't always the way at Microsoft. It's just been a super impressive thing all around. So, wait, I can do Kinect from all the way over here with my finger. Bloop. Yes, huh? We're really advancing the technology. You see that? So I just want to say, and I know this is a shameless plug because I'm here doing a talk at the MSR Summit thing, but MSR is pretty darn awesome. And it's it's unbelievable to me, again, that this stuff works and that people actually had the knowledge and the wherewithal to pull something like this off. And, I'm very cognizant of the fact that just as a creative person, I joke around about it, but that really is all I do is make up some stuff on a slide and in a PowerPoint, and then, hey, I know it has something to do with infrared, but I don't really know, how to get any of this stuff working. And it's wow, it's just been so liberating as a creative person to get to work with everybody at MSR, the technology that everybody's put together, the things that you've been able to pull off that give us the tools that we need to do an awesome creative job on the experiences. It's just been the most fun experience of my entire career. And, I just wanted to give a big hey, round of applause to everybody out there at MSR. It's been awesome working with everybody, and it's just amazing what you can get done. And then the last one, bloop. This is a funny thing, Kinect, while we are shipping this fall, we're really just at the very beginnings of our learnings with Kinect. And it's new technology, it's new design stuff. And, I am just super excited that, the Kinect platform and technology is going to evolve over time. There's going to be more cool stuff that we can do with it. And so hopefully there'll be more great technology from MSR that some creative person like me can make up a slide about and then we'll be able to play with later because it's super fun. Bloop. And the last thing, and I don't even know how appropriate this is or not, but I'll just say this. It's great working at MSR, or working at Microsoft and getting to work with people at MSR. I didn't really, when I first got here, even know what MSR was or, who people are in MSR or what they're working on. And it's been fun to get to know a small set of the people who've been working on the Kinect stuff. But all I can say is if anybody wants to ever chat about stuff that's going on with Kinect and what we're doing with it creatively or technology that people think are exciting that they wanted some kind of PowerPoint slides or videos made around that a creative person like me could do. I just think it's super fun getting to look at all the technology that's going on in MSR and all the research products. And if anybody ever wants to like just brainstorm any, experience stuff around any technology, that's my email right there at ku.@microsoft.com. And so just feel free to email me. It's great to hear from any of you, or if anybody just wants to reach out and introduce themselves, talk about Kinect, would love to do that as well. So that's I'm 3 minutes over, which is a world record for me because I talk a lot, and so usually it takes me longer. But I did want to bring out somebody who could give you a better explanation of how all the technology works and what went on with the technology process besides hey, it's the magic of infrared. So with that, we'll bring out Mr. Fitzgibbons. So you want to come on out?
Thank you.
Cool, dude. Enjoy.
Thank you. Thank you, Kudo, for bigging up MSR like never before. Well, welcome, everybody. I am going to talk a little bit about the process of moving these ideas into product. And I'm going to talk, before I begin, I'm just going to remind you a little bit about how MSR research turns into products in some other ways. So let's take, for example, I know you've all had some very exciting computer game footage and so on, but I know that what you really want to see is a SIGGRAPH paper, because that's the most exciting thing that can happen to us. Here's a SIGGRAPH paper, SIGGRAPH 2004. Some of my colleagues showed how you could draw a rectangle around an object in an image and automatically pop it out. And we thought, wouldn't that be very useful in PowerPoint? What if, for example, you could have an image like this, and then you could go into PowerPoint and say remove background and then click. Wouldn't that be a useful thing to have? So as you can see, this is running in Office 2010. And this was a sort of traditional MSR technology transfer, where it took us a long time to make the research paper robust enough that we could ship it to the numbers of people who use PowerPoint. And that was a tremendous success for us. Something that took even longer to get to fruition was, as you may know, Simon Peyton-Jones works with us in Cambridge. Simon Peyton-Jones has been a proponent of functional programming and Haskell for, let's say, over 20 years. About 10 years ago, one of our researchers, Don Syme, created a programming language called F#, which is a functional programming language following some of those principles. And in 2010, Visual Studio has released, and now F# is one of the main languages on this Microsoft platform. So this is essentially, you could think of it as decades of research coming to fruition, in the sense that now what we tell our students about functional programming is being told to programmers all over the world. So this is the type of success that we love at MSR, and we don't expect things to happen quickly. Well, about 10 years ago, my boss, Andrew Blake, worked on the problem of tracking human body motion. And many people in the computer vision field have worked on this problem. And it's been something that's excited us and that we've wanted to solve for a very long time. So this is a picture, pictures from a paper in 2001, where they're demonstrating that they can track this ballerina's motion quite convincingly. They could do that not at real time, and it only worked on a very small number of motions, but using a sort of search-based strategy, they got somewhere. The problem was that the search would have to be over a space of, let's say, 10 to the 13 body poses, and we didn't know then, and we don't know now, how to make that work. So more recently, people have looked at a regression approach. They say, hey, how hard can this be? You've got an image, right? It's just 1 million numbers. You've got the pose, which is just, say, 27 numbers, the angles of every joint in the body. Surely we can just find this function f, which performs this mapping from R100 to R27, and run it on every frame, and that'll be fine. And that approach was, it got us somewhere. I'm going to tell you a little bit about some of the problems with it, just so you can see, what the community has been doing, the computer vision community has been doing on this problem. So the problem statement is pretty simple. You get a set of training data, so Z1 represents the images, and I'm calling these a vector in R100 because I believe I can compress the image down to 100 numbers in a plausible way. And coupled with each image that you extract, you manually fit a CG model to the image to obtain a vector of joint angles, theta. So we've got some input images and some output thetas, and I'm representing them on this plot. I'm saying, here are all the images. I'm compressing 100 dimensions into one here. So this dot represents a certain image joint angle combination. And all we're going to do is fit a curve. And if anyone tells you machine learning is something other than fitting a curve, well, of course they're right, but effectively that is what machine learning is. We're going to fit a curve, and then whenever we get a new image, represented here by the object silhouette, we're going to read off the value on the curve and render it to our computer graphics system. And that's going to be the regression view of human body tracking. There are some small complexities. You don't normally want to give a precise answer. You want to give a probabilistic answer. So instead of returning exact answer, I return a probability density. Body parameters conditioned on the image. So is this ever going to work? Well, there are a couple of obvious problems. The first problem is that for a given silhouette, you can have multiple answers. So this silhouette may well be consistent with this pose or this pose. This one is probably slightly better, but the arm is wrong. They're both equally wrong. Okay, we know how to solve that. You don't return an answer, you return a probability distribution, and the probability distribution might have two humps. So that's fairly straightforward. We know what to do. In terms of how we implement this mathematically, we're saying that instead of this simple mapping a function from z to theta, we end up with this sort of multi-valued data. But that's easy. We can condition on the new image, find our new probability distribution, and present that to the user. How do we do that? We fit a joint density to the data, so we model the training data jointly in theta z space instead of learning a function. And now, for each new image, conditioning on that joint density gives us some hypotheses as to where the body is. And over time, we filter these hypotheses to present the most likely, most probable answer to the user. So that's all very fine. But I said we had training data a bit like this. I said that, but we're not in 2D, we're in 127D, so the data looks more like this. And if you run a sensible estimate of the joint density on this data, I don't think you can complain if the machine gives you this. I think this is a perfectly reasonable assessment of that data. So the problem is, how are we going to get more? We can't get more of that data. It was very expensive to label all those images. We expended all the effort we believed we could. We burned out enough grad students getting that data. So we're not going to do any more, being ethical people. What we can do, so what's hard to get is images with labeled joint angles. That's difficult. What we can do is get more images, right? That's not a problem. You just capture lots more images. And what we can also do is use motion capture to get a lot more samples of joint angles, but without the associated images. And now what we find, we can capture so many of these, it's as if they give us the marginal statistics of this distribution. And then if we look at the marginal statistics of the answer that I said we couldn't possibly criticize, we'll see that the blue curve here, the marginal statistics of this distribution, don't match the marginals we got from the unsupervised data. If we require the marginals to be consistent, we get the right answer. So although I had only the same number of joint space training points, I was able to get the right answer by incorporating these unlabeled samples that just came from, they're much, much easier to collect. So that's great. So that's a nice little academic story. We all loved it. We implemented it, and we ended up with a video like this. So the input is on the top left. We turn the input into a silhouette because that's the thing we believe we can reliably do with the video. We represent the silhouette by 100 points around the boundary, or you can think of it as 100 points around the boundary. We learn the mapping from those 100 points to R27 to the joint positions. And we demonstrate that we've done something by animating a computer graphic character to follow the input object. And we've locked the waist, not the feet, which is why he's performing this peculiar motion. And you can see that although he's running fast here, he's running a little bit slow here because there's a lot of heavy filtering on the data. So we were very happy with this because it really dealt with the problem of having a wide range of motions. We weren't restricted to, even that ballerina looked like she was executing a wide range of motions, but the system had been trained on ballerina motion before. Whereas here we could deal with the range of motions that maybe you might imagine would occur in the real world. but we have a lot of heavy filtering, and it was extremely far from real time. So that's 2007. And, you know, this sort of represents maybe the state of the art in human body tracking at that time. So in 2008, someone called us from Xbox, and they said, hi. They noticed that Roberto Cipolla here had been involved, who's an academic at Cambridge, had been involved with a lot of these successful human body systems, both working with us at MSR and working with his collaborators at Toshiba. So they knew they couldn't call Roberto, but they could see that one of Roberto's students was working for us, so they called Jamie and said, we need a body tracker, and you know, it's got to be good enough to play video games. So that means it's got to do a wide range of motions, cover work on a variety of people. It's got to be extremely agile, because that's what the video game is going to be like. And we weren't even real time, and the requirement was 10 times real time. You can only use 10% of the Xbox, because it's not going to be much of a game if the Xbox is spending 99% of its time tracking your pose. And we wanted to work for multiple players in the scene, so you're going to have more occlusion. So, but they said, you have got a 3D camera. So we looked at this for a little bit, and being intelligent computer vision people, we said, well, I can save you a lot of time. That is not going to happen. That is absolutely not going to happen. And then they said, well, you know, some of our games programmer guys have been trying to do this for a while, and, you know, they sent over this video. This is what we've got. You know, it's not that great. And they sent us a video of the most amazing body tracker anyone had ever seen. It was, no one in the research community had dreamed of anything this good. Running at double real time, extremely agile. Just, you know, it was like doing the thing that it was supposed to do, except it would lose track. So you had to start every frame in this special position, and then it would track you fantastically well for maybe 10 seconds, and then it would sort of crumple up and get lost. So this was incredibly inspiring and gave us some idea that we might be able to solve the problem. So what do we do? Well, the first thing we did is said, however you're going to do this, that this program had been written by someone who sat in front of his machine and just sort of typed main and then continued typing until he had a working system. It was robust because it worked on people of different sizes in his office, but it failed worse on those people. So our first idea was, well, the first thing you're going to need to do is get about 1 million images worth of training video, training and test video. So the Xbox team sent a team of people to households in, I think, 10 countries, and went into their living rooms and said, pretend you're playing on this video. And they just captured terabytes of data of people playing on this system that didn't exist yet. So, but we then had data of the different sizes of living rooms, the different sizes of people. We also, I told you the semi-supervised story because it's a nice academic story, because in those days we couldn't use computer-generated images, they weren't realistic enough. Well, in this case, we were able to go to a Hollywood motion capture studio and say, can you generate us 1 billion computer-generated images of humans in different poses, with different clothing on, with different hair, with all of this working? And of course, these guys can do that. So something that we weren't able to do in an academic setup. While this was going on, we continued to have a think about what we were doing. Jamie Shotton, the researcher who was involved, had a lot of academic work that he was still doing. So, for example, he was working on this problem. He was working on the problem of taking an image and automatically labeling every pixel in the image as one of these 20 or so object categories. And this is an area in which computer vision has been making, I think, exciting progress recently. We sometimes call it object recognition, or you could call it some sort of labeling problem. But we're really doing quite well at taking images like this and labeling them with the identities of the object. Jamie and his colleagues were able to make this real time. So I'll just let this go through a little bit. So real time, they didn't actually take a camera out in the field. But because of the way the system works, it's actually a valid test to do what they're doing here, which is point a webcam at the screen. And then the system is going to show us that it can label sheep, grass, cows, etc. In real time. Now, we weren't doing this because of a top-secret Microsoft agriculture project that we had been called about, where we realized cow recognition was going to be a crucial component. We were doing it for the obvious reason that you do anything, which is we didn't believe it was possible when we started, but other people in the computer vision community had shown that it might get there. So we could build a system which could do this real-time recognition. Now, at the same time, we have this body tracking problem. So obviously, we did what researchers tend to do. We think, I have a hammer. I've been applying this hammer to the object recognition problem. Perhaps I can apply it to the pose recognition problem. So what Jamie did was we generated some training images. So these are the images that are simulating what will be acquired from the Xbox camera, from the Kinect camera at runtime. And we decided we would treat it as an object recognition problem. We would try to train the system to take images like this and generate images like this, where every pixel is labeled with an arbitrary integer saying what body part is underneath that pixel. And that was the key idea that meant that in any frame, instead of having to start the tracker in this fixed position, in any frame we can generate hypotheses for where the body parts are completely independently. So if you fail in one frame, you don't fail in the next. Implemented, then there was some typing. And it was implemented on the Xbox. And what we do is make a probabilistic classification of each pixel. So each pixel is represented by 32 numbers, each one being a probability of being that body part. So when I'm in this position, I'll get left hand probable, right hand probable, and I'll have the same rating for the right hand. So it says it's a hand, I don't really know. If I'm in this position, it tends to be better. You have a probabilistic model of what's going on. And then you do the same old story with the filtering. So over time, to generate a consistent skeleton that maps that matches those probabilities, you can return a body configuration. And here I can show you sort of the debug screen of the system in operation. So the grey dots here are the raw 3D data that comes into the system. This is the body part classification. And then this is the three-dimensional shape that is computed to be most consistent with those body parts. And effectively, once we had turned it into this intermediate step, it just became a machine learning problem. Not the most easy machine learning problem in the world. We had millions or billions of images. And the classifier that we used, we went back to the 60s, because that's always a good place to find things that work, and we used a decision tree classifier. The decision tree classifier has effectively millions of classifier parameters. The training algorithm for the decision tree takes each datum, each pixel, and throws it randomly. You can think of it as throwing it randomly left or right. So every sweep through the data completely randomizes your data. You do not have an embarrassingly parallel situation. But luckily, at MSR, as Tony called out earlier, people are working on complicated parallel programs, and we were able to use DryadLink to get prototypes of this up and running extremely quickly. And DryadLink was extremely helpful in getting that sorted out. So, what do I conclude? We know machine learning likes hard problems. We hear this all the time. We hadn't believed how hard, well, as I said, we thought at the beginning this was a certainly impossible problem. Later we discovered it was only hard. The games programmers are amazing, not just in taking one's MATLAB or C# code and converting it into C++ that runs the way, when we used to write code, we used to write it really fast. The games programmers can also invent huge swaths of the research just by sitting down, thinking hard, and working. And I think the most surprising part of this story is that it was the blue skies research, the object recognition that we were working on, that actually went to market between September 2008 and Holiday 2010. I'll leave you with just one more announcement, which is at Microsoft Research Cambridge, we've been working a long time on machine learning, large-scale machine learning for video games. The TrueSkill system for match selection in Halo is another output of ours. The Bing advertising engine is something else we've worked on. Recently, we've packaged up this research because it's kind of hard to write these machine learning algorithms. It can take weeks. You need to get trained people. So just at the end of last year, we've launched Infer.net, which is a free software package which allows you to implement some of the latest machine learning algorithms extremely quickly in a probabilistic programming framework. So with that, I would like to thank you, and we're open for questions. So there are mic runners. So there's one at the back. Two.
So this may have become less of a need given the novel way you had of recognizing pose, but have you considered designing a Kinect game that tricks people into assuming certain poses so that you can photograph them and send them back as training data?
So, I mean, it's stuff, we've been doing a lot during our kind of beta testing for sure is, not even necessarily designing a game around the poses, but just collecting real human data from people's living rooms and such. And especially as, we try and get stuff ready for launch, the games where poses we're most interested in testing are surprisingly the ones for our launch game. So that kind of works out fairly nicely. But yeah, it's been a lot of, it's funny, just like you were saying before with the original work, it worked really great for the person who programmed it, and then the farther you got away from whoever coded it, the worse the results were. And so, I've been working really hard just on getting stuff in actual people's houses, not only here in Redmond, but all over the world, and getting all different people doing the actual launch games themselves. So.
Just to get an understanding of what's involved, supposing I wanted to create a Kinect program that acts as a conductor of a symphony orchestra, could you outline how I'd go about doing this and how long this might take, and what kind of programming skills would I need to do this?
So, I mean, at least from the design side, and this is something I just really believe in, is kind of like the method acting version of game development, where it's like, it's hard for me because I don't know enough about conducting a symphony orchestra to even know what direction to tell you, besides that somebody's kind of going like this a lot, right? And so, that's always to me the first thing is just going and learning how the heck somebody who's conducting an orchestra does their thing. And then from there, getting that to work with Kinect, I bet would actually, with the state of where the technology is, be one of the, be as straightforward as anything could be in a new technology and new medium. I mean, there are generally the person's always standing the same direction and doing very similar motions with their arm, and there isn't too much, spinning around or occlusion or the crazy motions that tend to give things trouble. But I mean, as far as how long it would actually take to make the game itself, I mean, it all depends on how much content you want to put in there and the fidelity of the content. But the actual just getting the Kinect stuff to work, once you learned what a orchestra conductor does, and you figured out how much you wanted to spend on, assets and the graphical, quality, and how much depth you wanted to go into his stuff, the actual getting the conductor's motions down with Kinect, I think, would be fairly easy.
Yeah, I mean, you would probably, well, I always have the same answer. You would run the Kinect system and see what joint angles it gave you for the motions that you were interested in the game. So you might notice that this angle and these angles are the important variables for simulating your problem. And I would just, use machine learning to map that onto the outputs you want, which is presumably something of the music or...
But you can tell, just staying true to my whole role in this program, don't worry, it'll be easy. Once you know the conductor thing, somebody will figure out how to make it work. So that's a much better answer.
System or in the future able to track fingers for other sort of UI applications?
Yeah, so I mean, your ability to track thing will exponentially degrade the farther you move away from the sensor. So like I have pretty big hands, and so within the entire range of the play space, my hands can be seen to some degree, but, we try and make, again, big feature of the program, stuff works. You get a little kid's hand, like from 3.5 meters away, it's super hard to track. And, we did a demo early on where it was like you were a safe cracker and you were sneaking around a house. And when we got you to the safe, we wouldn't move the safe close to the TV from the game's perspective until you move close to the sensor. So while you're standing there, the TV's off in the distance, you could kind of creep up like this, get right next to the sensor, and then the safe comes up to the point where, okay, now that the sensor can actually see my individual fingers and do stuff. So it's not part of the platform itself, but it's stuff that just as somebody making the experiences, if you create a design that's smart enough to work around seeing the fingers at a far distance, and you want to spend the time to coding that up yourself, you can get the finger tracking going within games.
In principle, you just retrain the body part system to be a finger part system, and it all works.
That sounded like a me answer. What the heck?
Well, I put in...
Just train the machine to do it. It'll work. Don't worry.
I put in principle in front of it. Effectively. There's a 3 over there for a while.
To what extent is the pose recognition system specialized to the movements and poses that you expect to see in a particular game?
So, I mean, it is the hard part because at the end of the day, like you look at a game like that river rafting game, there are some motions that are going to be made, like the jumping or the moving left and right. But then really people can do with their bodies whatever they want. And that's like a real kind of core creative principle, is just letting people do what they want. And if anybody who's seen like our Ricochet demo, the one where you're hitting a bunch of balls, there really isn't any set motion. And so some basic things that people will be doing that we try to optimize around and teach that machine learning thing to like actually track those things. But at the end of the day, you need to, on the game side, it needs to work robustly no matter what the player's body is doing. So there's certain things the games will do that you optimize for, but you still have to like cover all the other cases as well, because really people can move their bodies however they want.
We on?
Number 2.
So one of the nice things that happened with the Wii controller is that the community essentially hacked it, produced an API for it, and then people like Johnny Lee showed what you could do with it, and it essentially got it off the games console. So one of the big questions I have is, lovely technology, it's cheap, it means that it could get out there. Do you have to be on the box?
I'll take this one.
Is there anything to open it up?
At the moment, we are heads down on releasing Kinect for entertainment scenarios on the Xbox 360 by holiday 2010. We are aware of the incredible, exciting opportunities that will be available to the community. And we really look forward to the creative world changing the future in the future.
Are you going to do it?
No, we really... it is true that no one is thinking about anything but getting it released on time. And it's flashing last question, please.
Last question.
Yeah. Oh, there's a 3 here.
Oh.
You talked about the game learning your movement. What about, but then you had the sort of total recall teaching you tennis. What do you think about the game for educational purposes to teach you to move certain forms? I
mean, I think it's one of the really exciting things about where Kinect can take gaming is really to start teaching you things that are real world skills. And we have a game called Dance Central that's made by a different company than Microsoft, but it's a dancing game. And so I got married a little more than a year ago, and I'm such a terrible dancer that I tried to ban dancing for my entire wedding. So no first dance, but I didn't even want anybody else dancing for the embarrassment of people coming up, well, why aren't you dancing and blah blah blah. Just cut dancing all out. And really, since we started working on that dance game, it's awesome because, I've actually learned how to dance now, so my wife's super excited about games now because all she knows is somehow it taught her husband how to dance, and that's awesome. And, I've lost 32 pounds, since I started working on Kinect. So, and it is these kinds of things that, you're starting to be able to get to a point now where learning how to play video games actually helps you with things in your actual life, both physical things and I believe, that could be used for straight up more scholastic education as well. And, just think about a game like Guitar Hero. If all the time I spent playing Guitar Hero, now I could actually play a real guitar that well, how awesome that would be. And we're just starting to get to that point now with Kinect where those things are possible. And so, we've put in that Total Recall video kind of because it was funny and it amused us, but actually it kind of worked out that came to pass. And I think that's just, again, it's just a super nice thing for gaming that people spend so much time playing games, and to have that time be value time versus, just purely entertainment time.
Right. Well, thank you very much. Thank you, Julia.